This week we're going to be looking at adding some secondary elements to our destruction simulation. By this point, hopefully you'll have a cool rigid body sim shaping up, and let's take a look at what mine looks like. So I feel pretty happy with how this is coming together right now. There are still some little things that could use fixing. For example, when some of the pieces collide on the ground, they stop and roll almost immediately, so some of them could really use some extra bounce, especially in this foreground right here. And the stuff that lands a little bit further back on the helipad I'm not too worried about. But things are looking pretty good, and this is a good point at which to start adding a lot of these secondary elements like the particulate debris and the dust. So we'll look at the particle debris first. So here I have the setup we talked about in week 4, where we're caching out the points that represent the simmed bullet objects. And then we're using a transform pieces node to drive all of our fracture geometry with those simulated points. The only difference here is that I'm unpacking the geometry before running it into the transform pieces node, because we'll probably need access to some of the actual geometric information that's been packed away for doing our debris emission. Now there are lots of different ways of setting up this emission, and I've done it countless ways on different shows, and I feel like my colleagues and I are always working out different types of layers to use for these secondary elements and different ways to emit them and drive them, but we'll take a look at a couple options at your disposal. Now, one of the most popular ways to set up the source is to create some scattered points on our destroyed geo, and we'll use that to source the actual particle points. So, for example, let's create a delete node, and we're going to delete out everything that's not an inside face. So I'll switch the delete node to an expression and type at inside equals 0. So now you'll notice it's deleting out all the outside faces, and then we can just scatter our source points on the inside faces, because typically when these things break apart, you don't need to see little pebbles and dust come off the surface of the object. It would really just happen on the cracks. So now that we have this inside geometry isolated, let's scatter some points on there to use for our source in our DOP network. We'll use a regular old scatter node, and once again I think I'll use the density instead of the total count. Let's start out with a really low density, say like 0.5, and I'm going to template our geometry just so we can see that as well. Now you can see the number of points that our sim is going to be creating at each frame. Now this is an awful lot of particles if it's going to be creating them on every frame of our particle emission, so we probably don't need nearly that many. So let's take our scatter density down a bit more. We'll go down to, oops, not 1, let's try 0.1. Okay, this is, looks like a reasonable starting point. It's still a fair amount of geometry, but let's run that into our PopNet and see what we get. So let's create a regular DOP network, and we can run our scatter node into the first input. You don't have to run it into the first input. You can also create a null that we reference from inside. It's just really personal preference. And inside here, we'll create a pop solver, and we'll create some gravity. I'll double check what I set the gravity to in my rigid body sim, but it was somewhere around 10 or 20 times the default. So I'll start at 10 for now. And then we'll need a pop object and a pop source. So that pop object goes into the first input of the pop solver, and the source goes into the third. Now this pop object, we can leave all of the defaults on this alone for now. And then on the source, this is where we set our most important attributes at this point. So we don't want to scatter points onto the surface of our source, because if you remember, our source is going to be all of these actual points, not a geometric surface. So we can use these points directly, and instead of scattering, we're going to emit from all the points. And this SOP parameter here enables you to point to the SOP if you hadn't had it wired directly into the DOPNet. But since we connected our source points to the first input of the DOPNet, we don't need to use that parameter there. Under the birth tab, I typically set the jitter birth time to negative so that it interpolates backwards instead of forwards. And then by default, it's going to be inheriting all of the attributes from our source particles. So if we go outside of our DOPNet and middle mouse on this scatter node here, you'll see by default it's already picking up some attributes from our original geometry. Looks like it's already getting a velocity, so we can use that just fine as it is right here. And then if we dive inside the DOPNet, you'll see this is where it's inheriting everything. And by default, it's going to use that inherited velocity as well. However, the way we have this set up right now, it's going to create all of these bits of debris on every frame of our simulation. So let's animate this so that it only creates this for the first handful of frames in our sim. Because after things burst apart, we don't need it to continuously create more and more and more debris. We just want it to create a bunch when things first break apart. So I'm going to go back to our start frame, and I'll set this to manual so it doesn't keep cooking. And there are lots of different ways to control this, but I'll do this by animating the density scale. I'm just going to Alt left click to set a key here on our start frame of 1019. And then for now, let's say we want this to emit up through frame 1025. We'll try that. So then we can set that parameter to 0, set another keyframe, and then I'll shift left click this to pull up the animation editor. Now by default, Houdini gives you these flat tangents on these curves, and I prefer, when doing things like this, to set it to linear, just so it's a nice straight interpolation from one keyframe to the next. So now with this scatter node visualized, if we turn on our updating again and go back to frame 1019, you should see lots of points, and as we step through, we should see fewer and fewer debris points emitted from our fractured geometry. You can see that starts to fall off as we get closer to 1025. And of course, before we run the simulation, we should make sure to set our parameters on our DOPNet itself. Right now, the start frame is 1000, which is the start of our timeline here. But let's set the start frame to 1019 instead. That's when the actual impact happens. Now I'm going to template my transform geometry and set the display flag on the DOPNet, and let's see what our initial pass at this simulation looks like. Now we're not getting any particle emissions happening now, so we probably made a mistake on our pop source. And yep, this geometry source here has to be set to use first context geometry, since we've connected the input scatter points to the first input of that DOPNet. Now let's rewind, and hopefully this time we'll see our particle simulation. Okay, cool. Looks like everything's working. Looks like our particles are indeed inheriting the velocity correctly. And these ones are falling straight down because they're emitting from an area that just has no velocity whatsoever. And things are working about like what we would expect at this point. Now usually I don't let this inherit 100% of the velocity. Usually I'll use maybe 50% of the velocity inheritance as a starting point. Now there are a couple ways to do that. We could either multiply down the velocity values in a wrangle node after the scatter, or in the DOPNet we could also reduce it on the inherit velocity slider on our pop source. So right now we have it set to 1, so it exactly inherits the velocity. If we set it to 0, then we should see no extra movement on them once our pieces start simulating. So now you'll notice in this version of the sim, we don't have the particles flying up like we did originally. Now they're just falling down with gravity without any of that upwards force from these pieces. So let me stop that and rewind, and I'll set this to that 50% that I usually use as a starting point. Now we also should set up some instancing on these particles at this point. We don't want to just display point particles, we'll want some actual geometry on there. For the moment, we'll just use a basic box, and we'll copy that to all the points with a copy node. So this copy node will take some geometry into the first input, and some particles or any points in general into the second input, and it'll copy this first input geometry to all of those points. So if I hide everything else and I'll ghost the other geometry and make it obvious, you'll see it's placing this cube on all of those points there. Now right now all of our pieces are getting the same size, so we'll want to make sure to break up that size a bit. And that's a good time to use an attribute wrangle node to set that size on our input points. So if we create that attribute wrangle, make sure it's running over points, and then we'll type at pscale to create a point scale attribute. And generally this will default to 1, so if we set it to 1 we should see no difference. But if we change this to say 0.5, you'll see the cubes are half the size as they were before. And now let's use a random function in order to vary this up a bit. So we can use our trusty fit01 function that we've looked at a couple times, and we'll fit a random number based on ptnum, and we'll fit that between, say, 0.3 and 2. Let's see what that range looks like. That's a pretty wide range. It looks like some of them are a bit too big here. That's getting into rigid body sim territory. And we really only want this to cover the tinier pieces. Looks like 0.3 and 0.1 is not bad. Yeah, we'll stick with that. 0.3 and 0.1 looks like a good starting point. And now we're seeing all of these points as well because we have our copy node displayed directly. If you want to turn off the display of those, one way that I do it is just create a null node afterwards, and I'll display that instead of the copy node, so that it's not displaying all of our points along with it. And then just to help this visually stand out a bit from our rigid body geometry, I'm going to add some color to this as well. Let's start with, let's see what maybe 30% gray looks like. Okay, now let's show all of our geometry, and we'll once again template our transformed pieces, and then let's see what this instance simulation looks like. And this time let's view it from our actual shot camera. Cool, we still have a ways to go with getting these secondary bits to look nicer, but you can see already it's really starting to fill in a lot of detail and really give us a nice varied scale to the effect and make this look a lot more believable. Because of course with such a big impact, you're not going to get just large pieces coming off of that. Now if we look at our first frame of our debris simulation here, you'll see that right now it's currently emitting from all of the pieces, and really we only want to emit from the pieces that are in motion. So we can add on to our delete statement here. I'm going to remove the template display and just show the results of our delete node. And if we go to the filter expression and add double pipe for an OR in our expression. So it's inside faces equals 0, or we'll use a length function to check the magnitude of the velocity. So that's simply length at v.x for x velocity, at v.y for y, and at v.z for z velocity. And then we'll say if that's less than 5, we'll delete those pieces. So right now all of our geometry is being deleted, and if we step through our simulation, you'll see that the pieces that are in motion are not deleted by that delete node, so we can emit some debris from them. And then if we once again display our simulation, we can see the different results based on that change. Now, I almost always do my secondary debris using kind of hacky methods like this. I find it works really well and it's quite easily controllable and achieves good results. And especially with all the chaos going on in here, we don't need to have the most elegant sim for our secondary elements. But there's another option to generate the source points that you can play around with, and that is the debris source node. So if we just drop in a debris source and wire our geometry into that, this has options to create source points along the edges or the surface. I would typically turn the edges to 0 and the surface up to something large. I don't know, it depends on your scene, but maybe 10 or 20,000 would be good. You'll have to play around with it. And the rest frame should be the start frame of your sim. And the lifespan I would set quite low because we don't want these things to emit for very long once they start moving. It's a pretty short emission time range, so maybe 0.1 or maybe even less would be good. So what this does is this will scatter points on the surface of the object. I'm going to allow editing of contents and then dive inside. And if we look at this scatter node here, to turn my updating on, you'll see it's scattering points on the object, and this is what it's using to detect when the points are separating from each other. And when they do separate, it'll indicate that those are good to emit debris from. And then there's a SOP solver in here as well that's going to run that frame to frame to frame to compare those distances and determine what will be used to emit. And this option is pretty cool, but I've never really needed to use it, and I just wanted to put it out there as an option that you can experiment with if you'd like. But yeah, usually I'll just do something similar to this little setup that I've shown you here. Now, before we wrap up this section on basic emission, let's take a look at the geometry that we're instancing to all of the particles. So right now it's just a cube, and in some cases cubes can work decently well. For example, when dealing with pulverized glass, sometimes I'll use lots of tiny cubes as one of the layers in that sim. But for this kind of debris, we want something a little bit more shapely for those pieces. So either a box or a sphere should suffice for that. I'm just going to display that box for a moment and zoom in on it. And let's show our wireframe. Right now there are no divisions on this thing. Let's add a few more divisions. We'll have to make it a polygon mesh first. And then let's add a mountain node to this just to break it up a little bit. So here you'll see that even just the default settings on the mountain node give us a fairly interesting piece here. And we can make a few different variations of this piece. We can use the same box, and we could duplicate the mountain a few times. Let's say maybe 3 different versions will suffice for this. So we'll make 3 mountain nodes, and we'll change the offset on each of them so they're not exactly the same. So make an offset of 100 on this piece and 200 on this one. So they're all unique pieces. They're all about the same proportions though, so maybe I would transform them a little bit, and just drop a simple transform node and scale one of the axes up a little bit, maybe the others down a little bit. So for this one, let's say we make it a little bit taller in Y, add 0.5 to that, and maybe scale it down on the other axes to 0.8. So it's a little bit taller and skinnier. I'm going to take this mountain down a little bit so it's not quite as extreme. Actually, no, it's fine. That'll be okay. And then I'll create another transform node on our third mountain, and I'll change the scaling on this one to be scaled, let's say up a little bit in both X and Z, and just down a slight bit in Y. So now we have 3 distinct pieces of geometry, all about the same size. Then we can merge those together, and after they're merged, let's just set some new normals on those to make them a little bit more hard-edged. On this normal node, vertex normals will be fine. If you increase this cusp angle, that'll soften those normals. If you decrease it, that'll make those normals pretty hard and give you a more faceted look. It's a little bit more obvious if we display smooth shaded instead of wire shaded. And the reason for this is when these little pieces are flying through the air, it can look nice for the lighting to kind of catch little glints off of these angular faces. Whereas if the normals are softer, you'd be less inclined to catch nice little glints off these edges. And for many cases, that little bit of nice lighting detail will help a lot. In some cases, you might not want that, like if you were doing bits of dirt clumps, you'd expect that not to be reflecting much light in this manner. But for most hard geometry type materials, I tend to like faceting my normals in this way. Now if we take a look at all of our instance debris, you see that's a lot of geo to be copying to all the points, so we'll want to make sure to use packed geometry for this as well. Now the copy node gives you an option to pack geometry before copying. I've just been in the habit of creating some packed geometry myself before I pass it in. So I'm going to display my normal node to keep the copy sop from cooking while we make this change. And I'll add a connectivity node to create a primitive class attribute. It defaults to point, so I'd set it to primitive, which will tell us which pieces are connected. And then we can use that to create a name attribute utilizing that connectivity information. So change the attribute name to name. That'll be a primitive of type string. And we're going to call this instance underscore at class. You don't have to put that class in those backtick marks in order for that to evaluate. So now if we look at the spreadsheet on that attribute create node and look at the primitive attributes, you'll see that all of our primitives have a name of instance 0, instance 1, or instance 2 for each of our 3 pieces. Then finally, we can pack that geometry based on this name attribute. So now we're down to 3 points and 3 primitives representing those 3 packed fragments. So if we display our copy node now, you'll see that happened super quick. It took almost no time for that geometry to be copied to all of our points. Whereas if let's look back at our geo here and disable the packed geometry, and then display this copy node. And it didn't take super long, but there was more of a lag, and the heavier these shots get, the more of a difference that makes, especially when it comes time to render. Because right now, it looks like we have 1,660,000 primitives. So it's a lot better to use this packed geometry, of course. Now currently, all three of our instance shapes are being attached to every point. So we'll have to set up our copy node to only use one of those at a time. Now to do this, let's select that copy node, and on the Stamp tab, we'll turn on Stamp Inputs, and variable 1 we're going to call GeoID. You can use anything for this name, it's up to you. And then the value we send to that is going to be based on the particle ID. So $ID, and we'll use the percent operation to find the remainder when divided by 3. Now because we're looking up the remainder of 3, it'll set this GeoID variable to either 0, 1, or 2 for each point iteration of that copy node. Now that we have that GeoID set up, we can use a stamped function to access it and make sure that we're only creating one piece of geometry per point. So if you create a delete node and drop that on our instance geometry that's running into the copy node, let's flip this to expression, and we're going to use an expression called stamp to determine which piece to isolate. So if you type in stamp, it'll give you a hint here that says the first parameter points to the node that we're referencing for the stamp. In this case, it's going to be ... for a relative reference to our debris node here that we're working within, and then /copy1. The second parameter is GeoID for the variable we just created. And then the third parameter is just a default value to use if it can't find this GeoID parameter. So we'll just put in 0 for that. Now this stamp function will be returning 0, 1, or 2, representing the piece that we want to use for the currently processed point. And one way to use that is to compare it to the class attribute that we've set up on our instance geo. Now if you look at the packed geometry, you'll notice that there's no class attribute at our disposal. But if we go to the transfer attributes option and select class, then we will now have this class attribute available, and we can use that within our delete node here. So we'll say at class equals the value returned by the stamp function. And that'll have to be a double equal sign for this expression syntax here. Now say, okay, this is looking like it's still multiple geometries stacked on top of each other because it's only deleting one of them. It's the selected value that it's deleting. So just flip the operation to delete non-selected, and that way it'll be preserving just one instance piece per point of geometry. Actually, as I'm looking at this, I'm thinking we maybe push this mountain a bit too hard. These pieces are a little bit too gnarly, I think. So I'd probably just back off on this mountain a little bit more than I did for this initial version here. Let's try cutting that to like 0.6. And yep, that's looking a little bit better. This looks a little bit more pebbly rather than just too crumpled up like it did a moment ago. I'd like to make one last note on this copy node here. If you middle mouse on it, you'll notice we don't have any velocity information on our geometry. And we do have velocity on the output of our simulation here. Use .NET points. If you middle mouse, you'll see it has velocity as well as a bunch of other attributes. So in this copy node, if you go to the Attribute tab and click on Use Template Point Attributes, it'll copy a bunch of attributes from our sim points to this newly instanced geometry. So now when we middle mouse on the copy node, you'll see it gets a lot of attributes here. It's probably more than we really need. So instead of transferring all of those attributes onto this geometry, Let's remove the star in this 2-point field here so it doesn't copy everything. And now if we middle mouse on here, you'll see that it's not adding all of those attributes. It's just adding this velocity attribute that's been specified in this add field here. And finally, I'll just rename my null node out instanced debris. And we can delete this color node because it's not really working on our packed geometry.